The best way to learn how to make a game is, in fact, by making one. Even if it's just by copying these videos, the first step is to get accustomed with the code syntax, understanding where to place the scripts, grasp how to assemble the scenes, etc. Copying is an excellent tool to make all this more natural. By the end of this series, we will build a game from scratch. The videos not only present the solution but also explain the reasons behind the chosen options. Let's start by revising the basic game structure. We are building a classic shoot 'em up where the player, who flies from bottom to top, has to annihilate enemies flying from top to bottom. At the end of each level, there will be a stronger and tougher enemy to defeat, the boss. We will also add explosive mines and power-ups to make the action more challenging. In Godot, sizes and speeds are based on a unit called px. We could associate this px with pixels, but it's not that simple. The combination of settings can be non-intuitive and complex. In Project Settings, under the Display window tab, we find settings that affect how the image is rendered on the screen and how the camera is portrayed in the editor. We should also have the Advanced Settings option enabled. Given the introductory nature of this series, I won't delve deep into the possibilities of these values. However, it is essential to understand that some settings defined here will influence the entire game. Therefore, they should be chosen carefully in the beginning to avoid corrections in scripts later on. The most critical points relate to how Godot will handle the image size. What we draw in the editor needs to be adapted for different screen sizes, ensuring that the player's experience remains consistent. If one player has a 4K screen and another has a Full HD, both should see the game elements in the same positions at the same scale. Another challenge is the screen ratio. Both 4K and Full HD screens have a 16:9 ratio, but other formats show more or less content on the sides. We should consider this when designing maps and interfaces. With all that said, the values we should adjust are viewport width and height, mode, window override, and the stretch settings. By default, px will be treated as pixel. Let's set the values for a common 16:9 format like Full HD. So the width will be 1920 and the height will be 1080. If we close the settings panel, turn off and turn on the camera again, the magenta rectangle will update to represent the new size. The scale of the elements will influence how they are depicted relative to this rectangle, but speed will not be affected. Here we have two options. Keep the camera at 100% and adjust the scale of all elements so that they fit the image as intended, or keep all elements at 1:1 scale and zoom in with the camera. Since we already have all elements drawn in the correct size relative to each other, we will opt for zooming in the camera. However, this implies adjusting or readjusting speeds later on. Back in the project settings, let's set the other values. As the viewport is almost the size of a common screen, and this might make programming challenging, we will code and test the game in a window smaller than the screen. In this case, we set 960 by 540 in the window override. This is half of Full HD, however, this would cut off the display image. What we want is for the render to be scaled down to this size. To do this, in Stretch, we set the mode to Canvas Size and Aspect to Keep. After closing the panel, we know that what we are seeing will be exactly what the player will see on another computer with a different screen size. As mentioned earlier, the player consists of a body and has cannons that shoot lasers. Let's start by building these elements, but first, since we need to control them, let's set up the input map. In Project Settings, under the Input Map tab, we can create actions and associate different controls to each one. For instance, Godot already has an extensive list of ready-to-use actions. If we call UI accept in our script, we are expecting the player to press space, return or enter. Since every game is unique, we will code our own actions. Let's hide the default actions to see better what we are doing. In Add New Action, we type Move Left and press Add or Enter to add it. Next to the action, there is a plus sign, allowing us to add keys or other commands that will trigger the action. To move left, we can add the A key and also the left arrow key. If, in the player's script, we change the if statement responsible for moving to the left to input.isActionPressed move left, we are telling the script to listen to the move left action instead of the A key specifically. This way, we can link the movement to any key without having to modify the script. It also allows us to potentially have a configuration panel in the game where the player chooses their keys, something that would be impossible if the keys were hard-coded directly in the script. There's yet another advantage. The action system can also detect when the player presses the key, holds down the key, and when they release the key. By using the methods input is action just pressed, input is action pressed, and is action just release. If we modify the script to use the input map with move left, move right, move up and move down, we will find that we can now control the ship using the WASD keys as well as the arrow keys. But the input map allows for even more. We can also associate the axis of a joystick to achieve analog control. This means that the speed of movement will depend on how much the joystick is tilted. Having access to the input map is similar to keys, but the way we implement them in the script is very different. The joystick axis has a value of 0 when it's in the center and a value of -1 or 1 depending on the direction. If it's tilted halfway, the value will be 0.5. This allows for gradual increase and decrease in speed. In the script, we have the following structure. We create a vector for movement with a value of 0, we modify the x and y value according to the keys, and we add the value to the position. When using analog axis, we can directly put the axis value into the vector and add it to the position. This is possible because we have a 0 value when we are not pressing any keys or joystick, so the position will increment by 0, meaning it will stay still. To get a value between -1 and 1 from two actions, we should subtract the negative from the positive. So, where we set the vector to 0, instead we introduce the axis value. In a vector 2, we can put two float numbers in the arguments. The first will be relative to the x-axis and the second to the y-axis. For example, in x, we put input.getActionStrength move right, which gives a value between 0 and 1 for the x-axis to the right side. However, if we tilt the joystick to the left, we won't change the vector. For this we need to subtract the input getActionStrength move left, which gives a value between -1 and 0. To sum it up, if the joystick is in the center, move right and move left will be 0, and 0 minus 0 results in 0. With 0 in the vector axis, there will be no movement. If the joystick is tilted to the left, move right will be 0, but move left will go up to -1. Now, 0 minus -1 results in -1. The vector will have a value of -1 and the movement will be to the left. As you might have guessed, if move right is 1 and move left is 0, the result will be positive and the movement will be to the right side. The same applies to the y-axis. We just can't forget that in Godot, negative values represent upwards movement and positive values represent downwards movement. So the subtraction becomes input getActionStrength move down minus input getActionStrength move up, because move down is positive In vector 2, the x and y axes are separated by a comma. In this case, I will organize the code on multiple lines for easier reading. Remember that spaces and new lines don't affect the outcome, as long as the commands and symbols are in the correct order. What closes the declaration is the semicolon at the end. So, movement is equal to a new vector with right side minus left side in the x, comma, down minus up in the y. When we add movement to the position, we multiply by speed, our variable, and by float delta, the frame duration. So, speed times delta will be in pixels per second. However, we shouldn't forget that the camera has a zoom value that is not 100%, and this changes the perception of pixel and consequently the speed. A question might arise here. Vector 2 isn't a float. How is this possible to multiply by a float? In this case, the compiler understands that we want to change both x and y axes inside the vector, and multiplies both values by speed, sparing us the task of unpacking the vector. The getActionStrength method also works with keys. If we don't press any key, the value will be 0 and -1 or 1 depending on the direction. However, we don't have the analog functionality. The response will be as if we were always pushing the joystick to the limit. Another detail I want to talk about is the way we are adding the movement to the position. We have position equals position plus movement. This is okay, but there is a way to simplify this command. If we write position plus equal movement, the compiler will perform the same operation as before, saving us from writing the full instruction. In reality, these two ways are equivalent. The laser is fired by the cannon. To do this, we will have to address several issues. First, we need an action to shoot. We can call it fire cannon and add the desired keys, in this case Ctrl, Space and one of the gamepad buttons. Now we create a second scene based on Node2D, which we name Player Laser, and save it in the Elements folder with the same name. Here we need to display the laser, and for that we are using a Sprite2D with the image All Sprites. We edit a region and outline all the lasers without having any margins. In Animation, in the inspector of Sprite2D, we configure 4 horizontal frames. This will indicate to the Animator player that the image has 4 frames for an animation, arranged side by side. In Sprite2D, we add an Animator player, which is the node that allows us to create and play animations. In the animation panel at the bottom of the screen, we select Animation, New. We can name it Laser Flying. We press Add Track and choose Properties. The animation player doesn't only do animations with image, any parameter can be animated. We choose the node that has the parameter we want to animate, in this case the Sprite2D, and which specific parameter, in this case the frame. By default, the animation lasts 1 second, but this value can be changed. What we want to do is add the frames to the track in the order we want them in the animation. With the cursor at 0 and with Sprite2D selected in the node tree, we choose frame 0 and press the keyframe button. Automatically the cursor advances the time of one frame and the frame parameter also advances by 1. We just have to press the keyframe again and again to the next frame until we reach frame 3. For the animation loop to work correctly, we have to limit the overall duration of the animation. The logic has image plus space until the next one. On the last frame we have to respect that, and we need to leave the space for the frame to be visible. The cursor is at 0.4 and that's the value we set for the animation duration. We also activate the loop and autoplay on load options. If we press play, we will see the animation being played. We save the scene and create a new one called Player Canon, also saved in the Elements folder. The cannon will have no image. It will just be a point, the point where the lasers are instantiated. To control this, we need a script. We create an inherit script from node 2D called Player Canon and add it to the root node. The functionality of this script is simple. When we press the key that activates the fire cannon action, a copy of the laser is placed where the cannon is. For this, the script needs to know what the laser is and which action will instantiate it. We declare a public variable of type packed scene called laser. It must have the export attribute so we can set it in the inspector. In the process method, we check if the fire cannon action has been activated with an if. Using input is action just pressed fire laser, we can detect when the action is triggered. To instantiate the laser, we follow 3 steps. First, we create a variable to hold the new element and, at the same time, we instantiate the element in that variable. Notice that var is a generic type, and when instantiating the laser, we define the type. Next, we give the new element a location. Here, we use the variable we created as a reference to the instantiated element. This refers to the node where the script is. Since the script is on the cannon, the global position will be the same of the cannon. Finally, we add it to the game tree to make it visible. This command looks for the root of the scene tree, which is level 1, and associates the new element with that node. This is crucial because we want the laser not to be connected to the cannon, otherwise the laser would move with the cannon, side to side, when the player moved. After saving, we return to the player scene. Here we place the player cannon scene at the tip of the cannon. We can duplicate and drag or simply add more cannons. The goal is to have 4 cannons on the player ship. If we save and start the game, we will see that when pressing space, the lasers are instantiated in the cannons. However, there are still 3 details to fix. First, the lasers appear on top of the ship and should appear below to look like they come from inside the cannons. Second, the lasers have to move upwards. Finally, they need to be removed after leaving the screen so they are not overloading the game's process. To fix the issue of appearing on top, we go to the player's Sprite 2D inspector and ensure that the Z index in ordering is set to 0. The higher the number, the more forward the layer will appear, and the lower it is, the more in the background will be sent. Thus, the player stays at 0 and the laser at -1, right behind the player. To solve the other problems, we need a script to control the laser's movement. We create a new script based on node 2D called Player Laser and add it to the laser's root node. We declare a variable for speed and another for a vector indicating the direction. Since y is -1, the direction is upwards. Then, as we did with the player, we add the movement to the position without forgetting to multiply by the speed and the frame time. If we return to Godot and test, we will see the laser moving up. The last step is to remove the lasers when they leave the screen. For this, we use the visible on-screen notifier to the node to inform our script when the element leaves the screen. This node uses a feature of Godot called signals. Signals are special messages emitted by nodes when certain events occur. Many nodes in Godot have predefined signals, but we can also define our own. We will talk about creating custom signals in another video. For now, the important thing is that the visible on-screen notifier 2D will emit a signal called screen exited as soon as it detects that the element has exited the screen. We want to listen to that signal and, upon receiving it, remove the laser. To do this, we add the visible on-screen notifier 2D node to the laser's root node. In the script, we include public void remove element, open close parentheses, open brackets, queue free, open and close parentheses, semicolon. And in the ready method, we had the getNode method looks for a node of type visible on screen notifier 2D with the name visible on the screen notifier 2D. The connect method is then called inside this node. The connect method expects two arguments, the name of the signal and a callable that reference the method to be called. The callable class is a way of Godot to ensure that the specified method exists and can be called, providing more security and flexibility in connecting signals. What we are doing is connecting the screen exiting signal to our method that removes the laser. In Godot, by selecting visible on-screen notifier 2D, we can define the area that will be used to detect the screen exit. We ensure that it covers the entire laser so that it doesn't disappear while still visible on the screen. We save and run with F5. It seems to be working, but to make sure, we can pull the detection box higher up and we will see the lasers disappearing still within the screen view. If everything is functioning as we expected, we can put the box back into place and save it. Copy the entire content of this lesson. Create the alien cannon and alien laser elements. Write the necessary scripts so that the alien laser moves downwards and disappears when it exits the screen, and so that the alien cannon fires lasers automatically every half second.